So as you guys are aware, I won't be in class today, so what I did was make a little video explaining the topic that you would normally be learning with me today. So what I'd like you to do, if you haven't yet, is download the notes and the homework for Exponentials and Logs Day 2 off of Blackboard, so you can follow along and fill those in during the video. What I'd like you to do first, once you have those, is attempt the Do Now assignment on your own. Once you finish the Do Now, you can come back and restart the video and check your answers. So in the Do Now, basically our goal is to graph this function y equals 2 to the x. So the first thing that we're going to do is fill in a table of values for that function. So we're basically just going to plug in different values for x and see what we get out. So if we plug in, let's start with the easy values. So if we plug in 0, 2 to the 0 would be 1. If we plug in 1, 2 to the first is 2. If we plug in 2, we get out 4. Plug in 3, we get out 8. So those are the easy values. So then going to negatives, so if you think about 2 to the negative first power, so remember that's just equal to 1/2. So it basically takes your 2 and then brings it into the denominator of a fraction. So when you plug in -1, you get out 1/2. When you plug in -2, so 2 to the -2, that's like 1 over 2 squared, so 1/4, and so on and so forth. So when we plug in -3, we get out a y value of 1/8. When we plug in -4, we get 1/16. And so now that we have all these points that are going to be on our graph, we basically just want to plot them. So we have the point 0, 1, we have the point 1, 2, 2, 4, 3, 8, sorry, these dots are a little bit off, -1, -1/2, or +1/2, -2, 1/4, so we're getting closer to the x-axis, and so on and so forth. So now that we have our points, we can just go ahead and connect them. So something that looks like this. Pretend that actually goes through the dots. Okay. So in number 2, so it's just asking you to look at some different exponential graphs and look at some similarities and differences. So what I was getting at in this one was, you'll notice that the shapes are all sort of generally consistent. They sort of all have this like general like curvy shape. They're all increasing over time. So when I say increasing, I mean as you go from left to right, the y values are going higher rather than lower. You'll also notice that they all have a common y-intercept here at 0, 1. So one difference to notice would basically just be like how quickly or how steeply they grow. So you'll notice that like this red one, 2 to the x, doesn't grow as steeply or as quickly as this orange one, y equals 10 to the x. So depending on the base, which is just this number right here, depending on the base, it'll grow more or less quickly. So let's just talk quickly about some characteristics of exponential functions. So first of all, an exponential function is a function in this format, y equals a to the x, where a can be any positive real number, just not 1. And so they have certain characteristics in common. So first of all, exponential functions in this format will always have domain all real numbers, and then they'll have range 0 to infinity. So looking at these samples down here, you see that you can plug in like any x value that you want, but you can only get out positive y values. So that's why our domain is -infinity to infinity and range is 0 to infinity. You'll also notice that all these exponential functions all have a horizontal asymptote down here at y equals 0. So the graphs all sort of level off towards that asymptote of y equals 0. Now, there's also this information about the function being increasing or decreasing. So if you remember back when we talked about increasing and decreasing in September, increasing means as you go from left to right, the function is sort of growing like this, going upward, the y values are getting larger. Decreasing would mean that as you move from left to right, the y values are getting smaller. And so as you can see with these examples, whether an exponential function is increasing or decreasing, it kind of depends on this number here. So when the base is a number larger than 1, like 2 or 3, notice that the graph is always increasing. Whereas when the base is a fraction between 0 and 1, notice the graph is decreasing. And so exponential functions will always either be always increasing, like everywhere on its domain, always increasing, or it might be always decreasing, and again, that just depends on the base. Another thing to notice about these exponential functions is that they will always have a y-intercept of 0, 1. Now we're going to be transforming them, so the y-intercept will change or move when we transform it, but they sort of start off with a y-intercept of 0, 1. So let's do a couple examples of transforming some exponential functions. So in this one, it says to identify the transformations that are required to transform y equals 4 to the x into 1/2 4 to the x minus 8. So this right here, the y equals 4 to the x, is your parent function, and we want to transform it into this transformed function. I just want to think about what transformations we're doing. Then we want to sketch a graph of the transformed function. So in order to do that, we're first going to graph the parent, and then we're going to transform it into this guy here. So the first thing we have to do is think about what the parent function looks like. So we're going to make ourselves just a little table of values, listing out some points that we know are on the parent function. So typically for these, we want to do about 3 points on the parent function. You can always do more if you want, but definitely you should have 3 points. So some of the easier ones to use would be, you could plug in 0, and you would get out 1. You could also plug in x equals 1, and you'd get out 4. And then I would always suggest doing a negative. So if you plug in -1, you'll get out 1/4. And so this gives us a few nice points that are on our parent function. So we can plot those on our graph. So we have 0, 1, we have 1, 4, and we have -1, 1/4. So it'll be really close to the x-axis. So this gives us 3 points that are on our parent function. Now remember that your original parent function will always have an asymptote of y equals 0 for exponential functions. And so you want to just draw on that asymptote there, and then our graph will look something like this. Okay, so this one is our parent graph. So the next thing that we want to do is think about what transformations we have. So we see we have 2 different transformations here. So we have this 1/2 gives us a vertical shrink by 2. And then the -8 is going to give us a shift down by 8. So let's do those transformations. Now, the same way that we did with rational functions, I would recommend first transforming your asymptote, and then after that transforming your points. So for the asymptote, doing a vertical shrink, that isn't going to impact it, but then shifting it down by 8 will. So we're just going to move the asymptote down 8 units. So 1, 2, 3, 4, 5, 6, 7, 8. So here's where our new asymptote will be. So we're going to do the points, and we're going to vertically shrink them by a factor of 2, and also shift them down by 8. So this point up here currently has a y value of 4. Vertically shrinking it by 2 will divide that y value by 2, or multiply it by a half. So instead of having a y of 4, it'll be down here and have a y of 2. And then we just want to shift that down by 8. So 1, 2, 3, 4, 5, 6, 7, 8. And that point will be down here. So then for this point currently has a y value of 1. So if we vertically shrink that by 2, it'll end up having a y value of a half. And then again, we want to move that down by 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it'll be down here. And then this guy here currently has a y value of a fourth. So if we vertically shrink that by 2, you'll end up having a y value of 1/8. So it'll basically just be getting like really, really close to the x-axis, and we move it down by 8. 1, 2, 3, 4, 6, 7, 8. So it'll be down here, but like really close to the asymptote. Okay. And so we can just connect our dots, make sure that our graph is leveling off towards the asymptote, and then this one will be our transformed function graph. So looking at part B, it's basically asking us to identify some different characteristics of the transformed function. So notice it says the transformed one, so we're looking at the pink graph. We're not looking at the blue graph, we're focusing on the pink graph here. We want y-intercept, asymptote, domain, range, and where it's increasing, decreasing, and constant. So as we talked about, the domain of an exponential function will always be all real numbers. Because sort of looking along the graph, we can plug in all these x values, all these x values, all these x values, like no matter sort of how far down here we go, how far up we go, we can plug in all these x values and we're getting out points. And so our domain is going to be all real numbers. And remember the way that you write that in interval notation is negative infinity to infinity. Now our range is restricted though, so remember the range is the possible y's you can get out. So notice that you don't get out any y values down here. You only get out y values up here, up above the asymptote. So our range is restricted. Our range can only go from -8 and then upward. So our range is going to go from -8 up to positive infinity. So that's domain and range. So our asymptote, we figured out where our asymptote was. It's just down here. So that's going to be the line y equals -8. And then, as I said before, exponential functions will either be always increasing or always decreasing, depending on what the base is like. So looking at this shape, we can see that as we go from left to right, the y values are increasing. So this one is one where it's increasing everywhere. And so we're just going to write down that it's increasing. So to say that it's increasing everywhere, we're just going to say increasing from negative infinity to infinity. So the only piece we have left is the y-intercept. Now, you might be able to tell based on your graph where the y-intercept is. In this case, it was at like 0, -7.5. Sometimes, like if your graph totally just lived over here, you might not be able to clearly see your y-intercept, or maybe you just don't remember when you were doing the transformations, like was this down at like -7.5 or -7.25. So if you're not sure for whatever reason, you can always just plug in 0 for x and see what you get out for y. That's just sort of our general strategy for solving for y-intercept, so that works here also. So to solve for our y-intercept, we're just going to plug in 0 for x and see what we get out for y. So we get y equals 1/2 times 4 to the 0 minus 8. So remember 4 to the 0 is just 1, so we get y equals 1/2 minus 8, which is -7.5 or just -15/2. So we can say that our y-intercept is the point 0, -15/2. Okay, so let's just quickly review the steps in this problem. So the first thing that we did was we graphed the parent function. We did that by just making a quick table of values. 3 points is fine. And then we plotted that parent function. Remember to include your asymptote, which should be at y equals 0, no matter what the exponential is. Then we're going to list out our transformations. We're going to do those transformations on the graph. And then based on only the transformed graph, we're going to list out our different characteristics. So you're going to ignore the parent function when you're listing out your characteristics. Even though it's on the same grid, we're really asking about the characteristics of the transformation or the transformed graph. Okay, so what I'd like you to do now is there are a couple more practice problems on the next page, so I want you to try those practice problems on your own right now before you come back to the video. Okay, so at this point, hopefully you have tried out the couple of practice problems, number 4 and number 5, so I'm just going to show you the answers. So for number 4, the parent function is y equals 2 to the x. So here are some points that are on 2 to the x. And then I just plotted those on my graph as my parent function. So like I have 0, 1, 2, 1, 1, 2, 2, 4, 3, 8, and then I have negative 1, comma, a half. My transformations are a reflection over the x-axis. That's when you have the negative out in front, and then a shift right by 5, because you have 5 being subtracted directly from the x. So you're going to do those transformations. So to reflect over the x-axis, let me show you some points. So like this point here, to reflect over the x-axis, that gets reflected over here, and then we move right 5. 1, 2, 3, 4, 5. This point here, reflect over the x-axis, ends up down here, then we move right 5. 1, 2, 3, 4, 5. And this point, reflect over the x-axis, comes down here, right 1, 2, 3, 4, 5. So that gives you your transformed graph, and then you can just fill in the characteristics. So for this one, the reflection and the shift right didn't actually impact the asymptote. That stayed the way it is. And we know that the domain for any exponential function is going to be all real numbers. The range is going to be different depending on what transformations you have. So this one, because it got flipped over the x-axis, the range is no longer 0 to infinity. The range is actually from negative infinity up to 0. And then, again, because you reflected this one, instead of increasing, the transformed graph is actually decreasing, because as you work from left to right, the y values are going downward. Now this is one where you would not be able to tell the y-intercept from the graph. Like, what is it? We didn't, that's not a point that we have on our graph. And so what you have to do is plug in 0 for the x, and then just simplify down and solve for y. So you end up with negative 2 to the negative 5th. Unless the negative 2 is in parentheses, the negative 5th only applies to the 2. So the 2 to the negative 5th gives us 1 over 32, but then it's negative. So our y-intercept is at 0, 1 over 32. And then here is number 5. So that one had parent function 3 to the x. So here are some nice points on 3 to the x. In this one, because the negative was on only the x, that's a reflection over the y-axis. And then the plus 6 gives us a shift up by 6. So we graph our parent function. Shifting up by 6 will impact the asymptote. The reflection over the y-axis doesn't, but the shift up by 6 moves our asymptote up here. So we end up with an asymptote of y equals 6. And so then let me just show you how the reflection impacted the points. So this point, when you reflect it over the x-axis, over the y-axis, that doesn't move. But then you go up 1, 2, 3, 4, 5, 6. This point, when you reflect it over the y-axis, moves over here, and then go up 1, 2, 3, 4, 5, 6, and so on and so forth. So you can do that for the rest of the points. Now this one, you were able to tell where the y-intercept was just by looking at the graph. It's at 0, 7. Domain all real numbers. The range starts from the asymptote of 6 and then goes up. So our range is 6 to infinity. And then this one is decreasing, similar to the other one. This one's decreasing everywhere, so we say that it's decreasing from negative infinity to infinity. So the next thing that we have to talk about is doing this when the base is a special number. So there's a special base called e, and e is a number sort of like pi that comes up in a lot of real-world applications, especially in science, but it just sort of looks like this like long, crazy decimal. So in the same way that pi is like 3.14159, blah, 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 the number e is this number. It's about 2.71828, but it keeps on going forever the same way that pi does. And I promise that this will come up in your future classes, both math and science. And so it's important for us to learn sort of how that graph looks and how to transform it. So the first thing we're going to do is try and graph the parent function, y equals e to the x, and think about what that looks like. So let's get a couple points on the parent function. So when we plug in x equals 0, we just get out 1. That one's easy. When we plug in 1, we get out e. Now that's going to be hard to, think about how that's going to look on the graph. But, we talked about how e was about 2.7-ish, so you're just going to use that as like an approximate value when you go to graph. And actually, we can just go ahead and fill these points in. So we have 0, 1 is a point, and then we have 1 comma e, and so e is about 2.7, so we'll go 1 comma and then about 2.7, so not quite 3, up here somewhere. So then to get a third point, if you plug in x equals -1 to the exponent, you end up getting 1 over e. Now, again, we said that e is like a little bit under 3, so like when you go to put it on your graph, this is going to be like 1 over 2.7, which is like pretty close to a third, and since it's a teeny tiny, fraction anyway, 1 over 2.7 and 1 over a third are going to look very close on your graph. So when you go to graph that, you're going to graph it around 1/3. Okay, so that gives you a few points that are on your parent function, and the asymptote is the same, y equals 0. And then you can just connect your dots. So this pink graph is your parent function. So letter B asks you to think about some transformations. So what transformations would transform y equals e to the x into this guy over here? So this one is actually just a matter of some shifts. So we see that we have a shift left by 3 and then down by 5. So I actually think instead of doing this on this grid, maybe I'll just plot the transformations on this grid. It might be a little bit easier to see. So feel free to do that if you want. So we're going to go left 3 and down 5. So shifting left by 3 is not going to impact your asymptote, but shifting down by 5 will. So we'll go down 1, 2, 3, 4, 5. So our new asymptote is going to be down here. And then we'll just go point by point and shift left 3, down 5. So this point will go left 1, 2, 3, down 1, 2, 3, 4, 5. So it'll be right here. This point is going to go left 1, 2, 3, down 1, 2, 3, 4, 5, and I'll end up down here. And then this point is going to go left 1, 2, 3, down 1, 2, 3, 4, 5, so it'll be down here. And so then you can just connect your dots. And so this blue graph is going to be your transformed graph. Okay. So for part B, we actually did up above. Did this one up above. Okay. So what I'm going to have you do next is I'm going to have you try and think about what those characteristics are for the transformed graph on your own, and then you can unpause the video and check your answers, but please do take a second to think about what do you think the characteristics are going to be first. Okay, so hopefully you have thought about your characteristics. So based on the graph, again, domain is going to be all real numbers, the way that it has been all along. The range is going to be everything up above the asymptote, so from -5 up to infinity. Your asymptote is down here at y equals -5. And then this is one that is, this is one that is increasing everywhere, so we say it's increasing from -infinity to infinity. So I'm just going to do one more example for you where the base is a different kind of weird number, where the base is a fraction. So let's start by graphing the parent function together, and then you guys can try the transformations on your own. So let's first think about the easy x values in the table. So if I plug in 0 to this function, I know I'm going to get out 1. So if I plug in 0, I'm going to get out 1. If I plug in 1, I'm going to get out a half. If I plug in 2, I'm going to get 1/2 squared, which is a quarter. So the negative exponents are a little bit trickier. If I plugged in -1, then that -1 is going to apply to both the 1 and to the 2. And so what's going to end up happening is the 1 is going to end up moving down to the denominator, the 2 is going to end up moving to the numerator, and we end up just getting out 2. Similarly, if you plug in -2, you're going to get out 4. If you plug in -3, you're going to get out 8. And so that gives you the first several points on your graph. So we have 0, 1. We have 1/2. And then 2, 1/4. So you're getting really close to the x-axis. -1, 2. -2, 4. And -3, 8. And so, again, you're going to have an asymptote of y equals 0. But notice that for this one, the shape sort of is going in the other direction. So instead of an exponential that looks like this, we're having an exponential that looks like this. So maybe I'll actually walk you through these transformations just because there's a vertical stretch, so you might forget how to do a vertical stretch. So the two transformations that are happening are a vertical stretch by 3 and a shift right by 8. Let's write that down real quick. And I think that just the way that I'm doing it, it'll be easier for me to do the transformations on this graph up at the top. So you can actually see the parent function while we're doing the transformations, but feel free to do it on the bottom graph if that's easier. So again, we're going to vertically stretch by 3 and shift to the right by 8. So the vertical stretch is not going to impact our asymptote because right now it's y equals 0, and we know that a vertical stretch by 3 multiplies any y values by 3. So if we start with y values of 0 along the asymptote and multiply those by 3, we still end up with y values of 0. So that asymptote is not going anywhere, and then even moving it to the right by 8 is not really going to change how a horizontal line looks. So our asymptote is going to stay where it is. The other points will move though. So remember, when you vertically stretch, any y value on your graph gets multiplied by 3 in this case because it's a vertical stretch by 3. So these couple points up here, when you vertically stretch them by 3, the y value is going to end up off the grid. This one will end up with a y value of 12 because right now it has a y of 4. This one has a y value of 8, so if you vertically stretch by 3, it'll have a y value of 24. So these couple are going to move off the grid. But this guy here currently has a y value of 2. If I vertically stretch that by 3, I'm going to end up with a y value of 6, which is up here. And then I'm going to move to the right by 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'll end up right there. So then the point 0, 1. So if I vertically stretch that by 3, I'm going to end up at 0, 3 because I'm multiplying my y value by 3. So that'll be up here. Then I move it to the right by 8. 1, 2, 3, 4, 5, 6, 7, 8. So it'll be over here. This point right now has a y value of a half where it was supposed to. It kind of looks a little bit too high to be a half, but pretend that it looks like it's a half. If I vertically stretch by 3, that'll be up at 3 halves, which is like here at 1 1/2. Then we move over by 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the point will be over there. This point, which used to be at a y value of a quarter, or it's supposed to anyway, supposed to have a y value of a quarter. So if we stretch that by 3, it'll be at 3/4, and then we're going to move to the right by 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we'll have another point just up here at 3/4, and then we can just connect our dots. Like this. So this is our transformed graph. Okay, so at this point, we kind of stopped in my classes where I was present in. We stopped and I just had them do the rest on their own. So there's one more example of listing out the characteristics. So for this one, you should actually list out the characteristics for the graph that you just did. And then on the next page, there's a couple more practice problems for you guys to try. So what I'd like you to do is try those practice problems, and once you feel comfortable, please work on the homework assignment. So I intended this video and finishing up the practice problems to kind of be your classwork, which is what you would do while I was out during the class block, and then I intended the homework assignment to be basically what you would do for your normal homework assignment. So tomorrow in class or whenever I next see you, I'm going to check both that you finished up this packet, the notes packet, and that you actually took all the notes and finished the practice problems. And then I'm also going to check the homework assignment, the day 2 homework assignment, which you can download off Blackboard. So I'll also be checking that as your homework. So checking your notes packet will be like your classwork from when I was out, and then checking the homework packet will be like your homework. So please make sure that you have both of those 2 things done. I will post the homework answer key so you can be checking your answers as you go along, where I know I wasn't there. But please obviously make sure that you use that resource responsibly. And if you have any questions, we can check in about those in class when I next see you. So I hope you guys have a good day. Let me know if you have any questions. Feel free to send me an email, and I'll see you tomorrow.